So, you want to know a little bit about Linux, huh? Well, I've got just a little bit to show you this time. I'm going to go from start, which is that famous symbol underscore start, where assembly programs usually begin, and we're going to go all the way to idle. Now, that doesn't sound like very much fun, does it? We're going to start and get to idle. Well, idle doesn't sound like it's doing anything, but actually it is a big thing because once you're in the idle state, you're waiting for something to happen. You're in the idle task and you're ready for the next interrupt task to occur. Now, if you notice on Windows, sometimes you look at the task manager or you look at the different tasks that are in there. All of those are separate things that are running all at the same time during this operating system. So if we can get to that point, then we can say, okay, I know all the bloody details that get to that point, and now we can figure out how the operating system can schedule itself. Header.s actually contains the start instruction that I mentioned before. But before it issues the start instruction, there's some memory locations that are going to be important. Now, this is an x86 processor, which is what Intel and AMD produce, and they always start out in 16-bit mode. So code 32 start is going to come along later. Now there's a fixed value in here, but that fixed value can be changed by loaders. Loaders can put in a different value there. A loader means the tool that's being used to build the code. Still in header.s, the entry point is where we actually start executing our in 16-bit mode. Now, our goal is to get to 64-bit mode. So there's going to have to be some different things that are set up here. Making sure that we don't lose sight of our goal, what is our goal? Our goal is to go from 16-bit to 64-bit mode. And we have to recall that this header has the code 32 entry start. So once we're ready to get to 32-bit mode, then we can get to that level. Now, maybe a little conversation about that would be helpful. What's all this talk about 16, 32, 64? I'm going to give you a quick history lesson, and believe me, it's going to be really quick. The Intel first computer on a chip was a 4004. It was a 4-bit chip, meaning that it read only 4 bits on each axis. Just 4 bits, not even a whole byte. And its address bus was only 12 bits. 12 bits is not much memory addressing. Then the 8080 came along. This was the first 8-bit processor. The 8080 had an 8-bit data bus so that you could access 8 bits at a time, and it had a 16-bit address bus. That gave you 64K of RAM or any other memory location to deal with. Then, what came next? The 8086, which is the x86 idea. X8 for the 8086, the 8286, the 8386, and into finally 64-bit processors of today. The 8086 had 16 bits of data access, so it was considered a 16-bit processor, and it had 20 bits of addressing. So when we start in 16-bit mode, that means that we are acting like this old-fashioned 8086 processor with 16 bits, 2 bytes at a time of data read, and a 20-bit address bus, which gives us one whopping megabyte of addressing space. Every x86 processor starts out this way. The 8386 has 32 bits of data access. So you're doing it rather than 2 bytes, you're doing 4 bytes at a time. When you every data read, you get 4 bytes at a time. And every address sequence that you get in 32-bit mode has a 32-bit address bus. 32-bit address bus, 32-bit data bus, which gives us an addressable range of 4 gigabytes. Now, there's still a lot of 32-bit processor software out there, but most of it's migrating to 64-bit because you can read 8 bytes at a time, and you have an addressable space which is in the terabyte range. Normally, the address pins are limited to 48 pins, so you can do 2 to the 48 to figure out how many bytes are addressable. 32-bit or protected mode and 64-bit long mode require some extra tables to be set up. A global descriptor table for code and data segments, and an interrupt descriptor table for interrupts. So each of these things has to be set up, and you'll see that those things occur in the code. As I mentioned before, we're in 16-bit or real mode, and all we need to do primarily is set up the stack. The stack pointer is going to be necessary if we want to do call and return instructions, and even more importantly, if we go into C code, every time you call a function, it has to use the stack to store the parameters. So a short little section here to set up the stack. We zero out that stack, and then we call main. So we're in a completely different file now, and we're in C code. Here's main function in C code, which is the typical entry point in C code, and we're going to perform these steps while we're still in real mode. So there is some very initial stuff that can be done with memory and keyboard, but main point is we want to go to protected mode. So you'll notice the very last step here is go to protected mode. Go to protected mode is we have this thing called the A20 gate, which is the bit in the control register that allows you to go to protected mode or 32-bit mode. We reset a coprocessor, mask interrupts, and then here we go. We set up the interrupt descriptor table and set up the global descriptor table. Those are the tables that have to be there or we can't perform our operations. So the very last step is protected mode jump. We're not in protected mode yet. Now we're in this assembly code file, and we recall that the global descriptor table and interrupt descriptor table are already set up, and we now are changing some things in the control register 0, which will put us into protected mode. And then we hard code an instruction because we're in 32-bit mode now. Now we're ready to do some initialization in 32-bit mode. We set up all the data segments and the stack segment. Even though we had a stack before, we've got to set it up all over again. Then finally, we jump to the 32-bit entry point. Now, if you recall, back in header.s, we had a start 32-bit code. So that register or that address is what we're going to now. We load it into the EAX register and it takes off from there. This function, startup 32, that's the address that was stored in that code 32 entry point on the very first header. Now it gets really quite involved because we have to do all these necessary steps so that eventually we can get to 64-bit mode. Here we're back to loading a global descriptor table, and this has the 64-bit segments in it. Once again, we set up another stack and load code segment from the current global descriptor table. Now notice the comment, prepare for entering 64-bit mode. We perform some operations on the control register. Now this is a different control register because this is specifically for long mode. And then we get complicated here. We build an early 4 gigabyte boot page table. We need the page table because we want to go to memory addresses which are greater than 4 gigabyte, which is what the 64-bit processor can allow us to do. So we'll set up a lot of stuff above 4 gigabyte boundary, above meaning at higher memory addresses. Now that the page tables are set up, we can finally jump to 64-bit mode. And the entry address for that is going to be startup 64. So we'll look for that. Startup 64. Now this particular file is in a directory called compressed, meaning that we haven't actually got the kernel part decompressed, which gets really complicated, but that allows the kernel to take up less space in a file, and also it speeds up execution time if we do that compression. Interesting to note that the kernel is a compressed kernel, but not all of it is compressed. The earlier steps that we've been executing so far were in the mode where it was uncompressed. The compressed kernel is now copied to the end of the buffer so that we can perform the decompression steps. The function extract the kernel will return the kernel entry point. Now that's the kernel entry point. Now we're actually got the kernel in there, so we're going to actually start running the kernel. Up to this time, it's only been set up. Remember that our mission here is to start up the kernel. So we're in a decompressed version of the kernel, so we go once again to a function called startup64 and look for the point where it gives us the entry point to start the kernel. Way down here in the code, we show initialize the code, and here's our entry point, x8664 start kernel. We're almost to starting the kernel, but first we go through the x8664 entry point to get this done. More initialization stuff goes on. See how complicated this gets. And finally, we get to this function called x8664 start reservations. We do start reservations, and at long last, we get start kernel. So this is where the kernel gets going. All this other stuff, the real mode, the protected mode, the long mode, all those things were just to get to this point, and we'll never have to come back to those. Finally, we start the kernel. Now, at this point, there is a ton of stuff, which kind of shows you why there's so many lines of code that supports the kernel. There are tons of initialization functions that have to be performed here. So eventually we're going to get out of this thing, and my whole idea is to get to the point where we can finally get to the idle task. CPU startup entry, and then there's a while one loop that means do idle forever. do idle forever. Now, idle can be interrupted by other tasks that are going on in the system, hopefully, or the operating system's not doing anything, but they always come back to idle because you remain in the idle task for as long as anything else is not operating. It always goes back to the idle. I hope that was instructive to you as much as it was to me, just to know how things actually got to that point. Now, if we're going to talk about the Linux operating system, then we'll have to do the task switching, which that's going to be a whole other topic. So hopefully I can get you closer to that. And if you didn't like this, well, maybe the next one will be a little bit more clear.